Hello viewers, how are you? Welcome to my channel Physics with Rams. So today we are going to discuss about capillary rise method, and we are going to derive the expression for capillary rise method, and the expression is represented as H is equals to 2t cos theta by r rho g. So before going to start this topic, those who are new to my channel, please subscribe my channel so that you can receive my notifications, as well as you can watch my previous videos so that you can clear your concepts, as well as you can solve as many numericals as you can. Let's start this topic. So here when we observe the plants, here the plants supply the food from bottom to up, or they supply the water from bottom to up by using this capillary rise method. As well as we know that the kerosene also passes through the pores of the cloth and it burns upwards. Not only that, candle wax also burns due to this capillary rise method itself. Now come to the case. We consider a very thin tube. Very thin tube. When this tube is dipped in the liquid, the level of the liquid may rise or fall down, which we had discussed in our previous videos. Let us revise this. Let us consider I had dipped the capillary tube in a liquid. Okay, if the angle of contact is less than 90 degrees, then level of the liquid rises to a height h. It rises to a height h. If the angle of contact is less than 90 degrees, then level of the liquid falls down than its actual level in the beaker, like this. So example for this case is impure water. So when we dip a capillary tube in impure water, the level of the liquid rises in the upward direction. When we dip a capillary tube in mercury, the level of the liquid falls down and angle of contact will be greater than 90 degrees in this case, which we had discussed in our previous videos. So based on this, now we are going to derive the expression of H is equals to 2t cos theta by r rho g. For this, we consider the impure water case. So here when we consider this, observe that the level of the liquid has risen to a height h. So observe that here a meniscus is formed on the surface of the water. Means when we consider a liquid drop, the excess pressure in the liquid drop is 2T by R, where T is a surface tension. And R is the radius of this liquid drop. So now based on this, here when we compare the pressure on the outside is P naught, atmospheric pressure, whereas the pressure within the liquid drop is represented as a P naught plus 2T by R. So now the excess pressure within the liquid drop is represented as a P naught plus 2T by R minus P naught, which is nothing but excess pressure. So here we get a delta P is equal to 2T by R. Now observe that here we have two cases, means we can represent the convex side as well as a concave side for a liquid drop. Observe that it is a concave side and this one is a convex side, convex and concave sides. So now as you observe this case, here we can represent that pressure on the concave minus pressure on the convex side is equals to excess pressure 2T by R. Pressure on the convex side minus pressure on the concave side minus pressure on the convex side is equals to excess pressure, nothing but 2T by R. So now when we compare this equation, observe that here we got a meniscus. So it is a convex side, sorry, concave side, and here we have convex side, pressure on the convex side. So pressure on the concave side is due to atmosphere, so we represent it as a P naught. And you observe that on the concave side excess pressure is acting, and on the convex side atmospheric pressure or pressure P is acting. So based on that, here we can represent that pressure on the convex side is equal to pressure on the concave side minus 2T by R. Pressure on the concave side is nothing but atmospheric pressure, so we can represent it as a P naught minus 2T by R. So pressure on the convex side is equals to P naught minus 2T by R. So this is the pressure acting at this point. Now let us consider a point at a height depth h. We know that as we move into the deep of the liquid, the pressure increases. So based on the height, the pressure at this point based on this equation can be given as P naught minus 2T by R plus H rho G. So this is the pressure acting at this point. If we consider this point as A, we can represent that the pressure acting at this point is P naught minus 2T by R plus H rho G. Now let us compare the pressure at this point along with other 2 points B and C. Observe that pressure at B is nothing but, since it is an open end, we can represent that atmospheric pressure is acting at this point, as well as we can also represent that atmospheric pressure is acting at point C. So based on that, here we can represent that pressure at B is equals to pressure at C is equals to atmospheric pressure. Whereas we had represented that pressure at A is P naught minus 2T by R plus H rho G. But when we compare this, observe that they are along the same portion, means they are along the horizontal. So based on that, here we can also represent that pressure at A is also equals to atmospheric pressure, since they are uniformly horizontal. So now when we compare these two equations, observe that P naught is equals to P naught minus 2T by R plus H rho G. Observe that P naught gets cancelled on both sides. So from this equation, here we can represent H rho G is equals to 2T by R. 2T by R. Whereas here we have to represent the height of the liquid level risen in the capillary tube. So based on that, here we can represent that H is equals to 2T by R rho G. This is the expression given for height of the liquid level risen in the capillary tube. So when we consider this meniscus, observe that here a meniscus has been formed. So when we consider this meniscus like this, the radius of the liquid drop is represented as R. So here this is the meniscus in the liquid drop like this. Now the radius of the meniscus, nothing but capillary tube, is represented as R. Now by using this, we have to represent the height of the liquid level in this. Observe that this small r and capital R makes an angle of theta. So here the triangle is like this, small r and capital R, and here we have an angle of theta. From this cos theta equals to cos theta equals to adjacent side by hypotenuse, nothing but small r by capital R. So now we have to represent the value of capital R, where capital R is equal to small r by cos theta. So now when we substitute this in this expression, the height of the liquid level rising in the capillary tube can be represented. So observe that H is equals to 2T by observe that R equals to capital R equals to small r by cos theta. So it can be represented as 2T cos theta by R rho g. So this is the expression given for capillary tube when it is dipped in a liquid. Based on the liquid level risen or fallen, here we can represent this equation. Take a screenshot, we will continue. Okay, now we are going to solve a numerical based on this capillary rise method. So now this problem is asked in JEE Mains 2019. Let's observe the problem. The ratio of surface tensions of mercury and water is given to be 7.5. So the ratio of a surface tension of mercury and water is T1 by T2 is equal to 7.5. And the ratio of densities is 13.6. Density of the mercury by density of water is equal to 13.6. Their contact angles are 135 degrees and 0 degrees respectively with glass. So angle made by the mercury is 135 degrees. And we know that cos 135 is equal to 1 by root 2. 1 by root 2. Similarly, here cos 0 is 1. Now, observe that it is observed that mercury gets depressed by an amount in the capillary tube of radius r1. So here if we consider that the mercury level has fallen down up to a height of h, from the initial level, then observe that the radius of the capillary tube is r1, while water rises by the same amount h in the capillary tube of radius r2. So when the capillary tube is dipped in water, the level of the water rises to a height of h. So observe that the amount of liquid level fallen in the case of mercury is h, and the amount of liquid level risen in the case of water is also h. Now we have to find the ratio of r1 by r2. We have to represent the ratio of r1 by r2. So radius of the first capillary tube is r1, radius of the second capillary tube is r2, and we know that h is equals to 2t cos theta by r rho g, where the ratio of the densities has also been represented as 13.6. Now from this r is equals to 2t cos theta by h rho g. Since we have to find the ratio of r1 by r2, we represent the expression as r1 by r2 equals to 2 by 2 gets cancelled. So here we get T of mercury by surface tension of mercury by surface of tension of water into cos 135 by cos 0. So I am writing it directly, 1 by root 2. So height is the same, so h gets cancelled, and ratio of the densities, since we get reciprocal, or we can represent it as the density of the water by density of the mercury into g also gets cancelled. So Let's substitute all the values in this expression. After that, surface tension of mercury by surface tension of water is 7.5. So here we can represent it as 7.5 into 1 by root 2 into density of mercury by density of water is 13.6. So we can represent it as 1 by 13.6. 13.6. Now observe this equation. Here we had represented as 7.5 by 13.6 root 2. When we simplify this, here we can find out the ratio, or we can represent it as 75 by 136 root 2. Now let's divide this. Observe that 75 2s are 150. So here we get approximately 1.9. 1.9. So now 1.9 into 1.4. 4 9s are 36. 4 plus 3 is 7. 9 1 6 6 2. So here we get a 1 by 2.66. So this is the ratio of R1 by R2. Take a screenshot. We'll continue. Observe the next problem. Find the radius of capillary tube when it is dipped in pure water and water has risen to a height of 7.2 centimeters. Here observe that surface tension of water has been given as 72 into 10 to the power of minus 3 Newton per meter, and we know the value of G as 10 meter per second square. So we know the formula for a capillary tube. H is equals to 2T cos theta by r rho g. Here we have to find the radius r. So observe that r is equals to 2t cos theta by h rho g. Since here he had represented pure water, angle of contact will be equals to 0. So cos 0 is equals to 1. And observe that height of the liquid level risen, water risen is 7.2 centimeters. So we can represent it as 7.2 into 10 to the power of minus 2 meters. And surface tension is T is equals to 72 into 10 to the power of minus 3 Newton per meter, or we can also represent it as 7.2 into 10 to the power of minus 2 Newton per meter. And observe the value of G is 10 meter per second square, as well as we know the density of water as rho is equals to 10 to the power of 3 kg per meter cube. So as we know all the values, when we substitute this, we can find out the radius of the capillary tube when it is dipped in pure water. Observe that R is equals to 2 into surface tension is 7.2 into 10 to the power of minus 2 into cos 0 is 1 by height is 7.2 into 10 to the power of minus 2, and density is 10 to the power of 3 into acceleration due to gravity is 10. Observe that 7.2 into 10 to the power of minus 2 gets cancelled. So R is equals to 2 by 10 to the power of 4. When we bring this 10 to the power of 4 to numerator, then R can be represented as 2 into 10 to the power of minus 4, or we can also represent it as 0.2 millimeters. So this represents the radius of the capillary tube when it is dipped in pure water. Take a screenshot. We will continue. Yeah, observe the next problem. If a capillary tube is dipped in water, the height of water that rises in it is h and its mass is capital M. If the radius of the capillary tube is doubled, the mass of the water that rises in the capillary tube is. Now we have to represent the mass of the water that has been risen in the capillary tube when the radius of the capillary tube has been doubled. Let us consider the radius of the capillary tube is r. Now in the second case, the radius of the capillary tube has been doubled. So when the radius of the capillary tube is r, the height of the liquid level risen is h, and by using the equation h is equals to 2t cos theta by r rho g. After that, height is inversely proportional to radius. So we can represent that h is inversely proportional to r. Based on that, h2 by h1 is equals to r1 by r2. Observe that r1 equals to r and r2 equals to r. Based on that, we can represent that h2 by h1 is h. h is equals to r by 2r. So r and r gets cancelled. So here we get h2 is equals to h by 2. So when the radius of the capillary tube has been doubled, the height of the liquid has been fallen to half of the initial height of the liquid. Now we have to find the mass of the liquid within the capillary tube. We know that mass is equals to density into volume, whereas density into volume can also be represented as area into height. Area of the capillary tube based on this radius can be represented as rho into pi r square into h. Pi r square h. Now mass of the liquid in the capillary tube by initial mass m is equals to, so m dash nothing but density of the water into pi into radius has been doubled, so we can represent it as 2r whole square into h by 2, h by 2 by rho into pi r square into h. After that, density gets cancelled, pi gets cancelled, whereas height h also gets cancelled. So m dash by m is equals to 4r square by 2r square. Observe that r square gets cancelled and here we get 2. 2 to the 4. Based on that, we can represent it as m dash equals to 2m. So mass of the liquid within the capillary tube when the radius of the capillary tube has been doubled is twice of its initial mass. Take a screenshot. We will continue. Observe the next problem. A capillary tube is dipped in water with its lower end 10 centimeter below the surface of water. So the capillary tube is dipped up to a depth of 10 centimeters. Water rises in it to a height of 5 centimeters. So water has been raised to a height of 5 centimeters from the surface. The pressure required to blow a bubble at the lower end. Here we have to blow a bubble at the lower end of the capillary tube will be. So now here we have to find the pressure required to blow the bubble. Whereas we know that pressure is given as P naught plus pressure due to the liquid drop, nothing but 2T by R plus h rho g. This excess pressure can be represented as 2T by R equals to h dash rho g. So in the place of 2T by R, we are going to substitute h dash rho g. Then pressure equation can be given as P naught plus h dash rho g plus h rho g. Observe that here we can take rho g as common. Then expression can be given as P naught plus rho g into h plus h dash. We know that the atmospheric pressure is given as P naught equals to 10 to the power of 5 Pascal. And the density of water is rho is equals to 10 to the power of 3 kg per meter cube. And the value of g is 10 meter per second square. Here h is nothing but the height of the Capillary tube dipped in the liquid. H is 10 centimeters and H dash is nothing but the liquid level rising in the capillary tube. So total height H plus H dash is 15 centimeters. So in terms of meter we can represent it as 15 into 10 to the power of minus 2 meters. So we can represent it as 0.15 meters. H plus H dash is 0.15 meters. So let's substitute all these values in this expression. Observe that 10 to the power of 5 plus 10 to the power of 3 into 10 into 0.15. 0.15. So now when we take 10 to the power of 5 as common, the expression can be represented as 1 plus 0.015, or we can represent it as 1.015 into 10 to the power of 5 Pascal. So this represents the pressure acting at this point in order to blow a bubble. Take a screenshot. Please give a like to this video, share this video to your friends, and don't forget to subscribe my channel.